By the way, our recordings, our archives has been taken down by request of me to the webmaster because of the space, and there were some other problems going on. So we're only going to keep the last 1, 2, or 3 weeks up there. So when this one gets done, that will go up, and the earliest one will leave. So if you need to see the show again, just do it in the next couple of weeks. So let me find what I need to find here. And we'll start our show. Get my pointer here. There we go. Okay. So this is a simple geology of the selected national parks. We, of course, don't have time to talk a lot about any of them, except I did highlight a couple of them because they're really, really special. So just as a reminder for everybody and the new folks on board tonight too, this is what we call our rock cycle. And basically, you know, we start with magma. Magma will cool into an igneous rock. It could have been lava on the surface, or stay magma deep within the earth and cool and become a igneous rock inside the earth. Basalt is a lava. Granite is a we call it an intrusive igneous rock. You'll hear about both of those tonight. Igneous rocks weather and erode. They turn into sediment. You glue sediment back together, it turns into sedimentary rocks like limestone, shale, sandstone. And if you put heat and pressure onto sedimentary rocks, they turn into metamorphic rocks, where usually the mineralogy may change, or just the texture of the rock may change by heat and or pressure. And metamorphic rocks can be heated enough, particularly in subduction zones along the plate boundaries, where that metamorphic rock will remelt back into magma. Now, igneous rocks can also go directly to metamorphic. Heat and pressure can be added and go right across here. Of course, the sedimentary and metamorphic rocks go back to weathering also. So there's sub arrows within this big cycle that's not really on here. Abundance in the crust. Igneous rocks are the most abundant rock in the crust. And sedimentary are actually the least abundant when we look at the entire crust. But if you look at the surface rocks around the world, 95% of those rocks on the surface are sedimentary. And 5% are igneous, and about 1% or less are metamorphic. So tonight with the national parks, you actually will hear all three being mentioned. And the geologic time scale, I'm not going to do too much on this, as far as I will throw some years out to you, or I might use we might use the word, you know, Jurassic, Triassic periods, but our national parks actually cover a vast, actually almost a whole part of this whole history, from 1 billion years old up into actually the Ice Age Pleistocene area. So the geologic time is actually represented well within our national parks. So the geophysical provinces of the United States, I'm obviously not going to read these to you, but we can break the country into physiographic provinces based on elevation, landforms, rock types, vegetation. Okay, and for example, where we are in southeast Pennsylvania, we're in at least I'm in the Piedmont area. Some of you are in the 24, which is the Valley and Ridge province, includes the Appalachians. Number 4 is the Blue Ridge. We do have several people that do live in the Blue Ridge. I don't know if they're here tonight with us, And of course, out west, we have all the other provinces too, the basin and range. But anyway, all these areas can be broken in into a different province. So how many national parks are in the United States? Anybody really know that answer? Depends how you look at it. Okay, you can divide it in a couple of different ways. For example, there's 64 national parks that actually have the name national park behind it. And believe it or not, there's a national park in all 50 states, plus our territories. I'm going to give you a question now. I'm going to answer it at the end. What was the last state to get a national park? I'm not going to answer that now. I'll save that until when we're done. So what state was the last state to get a national park? So there's actually 423 total properties that fall under the National Parks Agency in the federal government. But most of those are historical properties, but they do not have national park behind their name. Okay, and they total about 84 million acres of land. So that's a lot of territory around the country. Our first stop is one of my favorites, Shenandoah National Park in Virginia. You might know it as the Skyline Drive. Maybe some of you have been on the Skyline Drive. It's a beautiful area, and of course, Shenandoah National Park is like the Skyline Drive goes through Shenandoah National Forest from Front Royal down to Waynesboro, Virginia. And along the way, there's a geologic story from 1 billion years to about 500 million years old. This is actually within the Blue Ridge province, and that's the same as kind of what we see in Pennsylvania around the Caledonia State Park area and Blue Ridge Summit area. But the rocks are a little bit older down here in Virginia. There actually is a geologic book on the Skyline Drive. I think the author was written by Badger, who's a college professor, and that is available online. It's really, really good. Gives you mileage markers to check out and what road cuts are what. Just one of the views from the Skyline Drive looking over toward Massanutten, or Massanutten, if you want to pronounce it that way, mountain. And a beautiful view, and of course, you understand the geology there. Old Rag Mountain, for example, is a mountain that's is granite. Granite, as I said earlier, is a intrusive igneous rock. This granite's about 1 billion years old. It represents an ancient continent. Some of you folks have been with us for a while now, have heard of the supercontinent Rodinia. This is actually crust of Rodinia that has shown up now within the Shenandoah National Forest. There actually is a geologic trail going up the mountain where you can actually get a brochure and it tells you at different stops what you're supposed to be looking at. In the geology.
Here, what is this? Granite equals 1. What is it? What is BYA?
Billions of years ago. Billions of years, yep.
And it's how do you pronounce that?
Granite.
Granite?
Yep.
1 billion years ago?
Yep. Here's one of the road cuts. It's it's about 12 miles south of Front Royal. This is basalt. This is actually with a volcanic lava, about 550 million years old. But you see the shapes are like a hexagonal. We call it a pillow lava, where this lava flowed into a shallow ocean, and it cooled very quickly, similar to what's going on in Hawaii today, and it has formed these hexagonal shapes. So it's called pillow lava. There's a couple of good road cuts of it along the Skyline Drive that you really can't miss if you're looking for it. So good volcanic activity, sedimentary rocks. You see the layering here, and you notice that there's actually two directions of layering in this particular rock, which is a sandstone. This is what we call cross bedding, where it tells us that this was in an ocean, two different directions of current coming onto the shore. If you go to the beach today and watch the ocean water, there's actually two directions that the water's coming in to make this cross bedding. So here's kind of angled the other way here, and horizontal up there. So again, a lot of the rocks that are not volcanic and are igneous in Skyline Drive, Shenandoah National Park are sedimentary in origin from an ancient ocean. So I just want to make sure that we're seeing eye to eye tonight. Okay, go out to Oregon, Crater Lake National Park. People that have been to Crater Lake and know how impressive it really, really is. This is the deepest freshwater lake in the country, 1,949 feet deep. And it's what we call a caldera, which means it's a collapsed volcanic cone, about 7,700 years old. And the big number that you'll see on these slides, that the first one actually is the annual attendance into that national park. So they had 535,000 visitors as of 2019. So 535,000 people visited Crater Lake. Freshwater lake, there is no outlet to the water. It's only resupplied by rain and snow melt sort of thing. Wizard Island, which sits off to the side in the lake, was a last gasp volcanic eruption of this mount. It was called Mount Zoma, and this was the last little gasp of it before it did collapse. So anyway, you can check out Wizard Ranch, Wizard Island if you get out there. Looking at the like a topographical map of the lake itself, you see the different peaks. Again, there's some other islands in the lake other than Wizard over here, and you can see the water depth here on the cross section. So, like I said, it is the deepest freshwater body of water in the United States. Move over to Hawaii. 1.7 million people visit the Hawaii each year. Of course, we know that it's active for volcanoes. The shield volcanoes that we talked about before with our couple of different programs. Shield volcanoes only erupt lava. The present day islands that are active are about 300,000 to 600,000 years old. And these volcanoes, Kilauea and Mauna Loa, for example, their base is actually at the bottom of the ocean. And what you're looking at is the top of a volcano, which is now one of the Hawaiian Islands. So the whole mountains, the whole volcano might be total of 60,000 feet high if you take it from the ocean bottom. And again, here's an example of how pillow lavas are being formed in Hawaii. Again, we can see this happening where the lava is flowing into the ocean, and it's cooling rather quickly, forming pillow lavas. So again, if we see it like on the Skyline Drive, and we see it forming at Hawaii, we can say, oh, that's how that happens, sort of thing. So, in fact, this is a pillow lava down here in the lower left-hand corner here in York County along the Susquehanna River. Lava tubes are really neat things. If they never visited a lava tube, they're all over the western part of the United States, and of course in Hawaii, where you had volcanic activity. This is where lava was flowing, and the outside of the lava body solidified, cooled first, and the middle part kept flowing. And of course, it ran out of its supply of lava, and it formed a hollow tube, very similar to a straw. And the only way to access a lava tube is in case part of the ceiling of one collapses, or there's actually an outside entrance to it. So the longest lava tube is 40 miles long, over 3,000 feet deep. So they're pretty incredible. Don't look for any cave formations because there aren't any. And again, a reminder how the Hawaiian Islands and the associated islands are being formed is by the stationary column of magma called a hotspot coming up through the mantle and the crust. And as the plate, in this case the Pacific Ocean plate, is moving to the northwest, new islands are being formed over a course of millions of years. I think here's the chain of islands. Hawaii's down here, and you can see the whole chain of islands made over that one hotspot, which is right here. So, and in fact, you see in the course of time, at one time, the Pacific Ocean plate moved north before it shifted to a northwest direction, where it's presently moving today. So that's how that can help us figure that out. Of course, the Grand Canyon. Many people visiting that. 4.7 million people in a year. They go see rocks. Basically, that's what I tell everybody is that people go on vacation to go see rocks. So incredible sequence of sedimentary rocks mostly. This kind of a cool picture I liked of lightning striking the canyon. But again, a very, very thick sequence of limestone, shale, sandstone, conglomerate. Down in the bottom of the canyon, there is a rock called a schist, which is a metamorphic rock. That's the oldest rock within the canyon. That is a metamorphic rock. That was actually metamorphosed before the rest of the rock formed over top of it. And of course, all these different layers have different geologic formational names to it. You see sandstone, shale, limestone, coming up through the sequence. And many of these rocks layers are fossilized. So you can actually tell the date from youngest to oldest by the fossil content. Here's another scheme of things. As you might be looking at a book, you see the millions of years ago over here. So the oldest rocks are about 1.6 billion years old in the Grand Canyon. And then you get into the sedimentary rock stuff starting about 525 million, all right up through. So on a geologic time scale, we're starting over here at the oldest, working right up through, and then this column should be over on the bottom of this one, and up into the Permian age is about the youngest rock on top of the Grand Canyon. So again, you see the horizontal layers. This rock has not been deformed at all by any plate tectonics or movement, strictly by they're being exposed by erosion, basically of the Colorado River. And the people who are brave enough to go out into the glass bottom observation deck, help yourself. I'll stand on the shoreline there and take pictures myself. So nice sunrises over the Grand Canyon, and this is of course the Colorado River, where the canyon was actually developed mostly by the erosion of the Colorado River through these relatively soft rocks until it got down into the schist rock. I just threw this in because it's kind of interesting if you haven't seen it before. A pair of Levi Strauss jeans. The 49ers, 1849 prospectors of California, wore these jeans to pan for their gold, and they actually were started because they built tents out of the Levi Strauss jean material. Also, they were so good of a jean they could build tents that were very durable. This pair, by the way, sold on eBay for $46,500. So, expensive pair of jeans. We move to Meteor Crater, okay, in Arizona, and it's 3,900 feet in diameter, 570 feet deep, and actually the ridge around the canyon, the crater, is 148 feet high. So this is about 148, 150 feet high, made out of some of the ejected material when the meteorite crashed into the crust. Usually it was originally known as the Rainier crater. Actually, not to confuse you, this is not a national park property. Technically, it is still privately owned by a family who have a foundation, but it is a nationally protected property of the National Park Service. That's why it's included in all this. So 50,000 years ago, this object, which is now estimated to be about 160 feet in diameter, traveling 28,600 miles, crashed into the crust and made what they consider one of the world's best preserved impact craters on Earth. I'm amazed if I go back here. I'm amazed that the meteorite did not hit the visitor center. You know, just ironic that the visitor center was missed through all this impact stuff. That was a little humor. Okay, never mind. Speaking of impact craters, in case you not know it again, we do have a Chesapeake Bay impact crater not too far off the coast in the bay down at Cape Charles, where exploration is still taking place in drilling to get to the object, find out if it's an asteroid or a meteorite, or exactly what it was 35 million years ago. And surely our part of Pennsylvania, wherever you are here, probably had some effects by this impact. We're going to move out to Michigan now, to the Isle Royale, Michigan island. This is a national park. Only 14,000 people visited the site in 2019 because there's no roads to it. You have to take a boat to get there. It's an island in the Lake Superior. Old copper mine district. These are all the major copper mines that operated on the island in mostly the 19th century. You can see the 1843 to 1893, it was about the time that the copper was being taken out. It is now a national park. Lovely trails to walk, lots of nature to observe, sort of thing. It's kind of a geologic interest park. It does have basalt, volcanic rock. That's where your copper is coming out of, actually. In the basalt, it does have sandstone and also another sedimentary rock called conglomerate. The basalt found on the island is the gemstone of Michigan. And this is what it looks like polished up, which sometimes you can find on the island polished by the glaciers. this area was glaciated at one time. So some of this basalt did get polished through the glacial movement. So the rocks on the island are 1 billion to 600 million years old, and the glacial deposits, of course, are much, much younger. So if you haven't never been there, put that in your calendar. Real neat little place to go. Don't expect a lot of services and a lot of fancy resorts on the island, because you won't find them. Okay, we have Acadia National Park. Actually, we had a request for Acadia. This is already in the program before we got that, but Acadia is really loaded with cool stuff going on. It has sedimentary rocks. It has metamorphic rocks. It got metamorphic, and it got igneous rocks. So sedimentary rocks formed from a very, very early ocean environment. Igneous rocks, pretty much the same thing. It had some volcanic activity and some igneous activity during its early millions of years, days ago. And a lot of these rocks got changed by heat and pressure through collisions of metamorphic rocks. So all within Acadia National Park, you have volcanic activity, you have ocean, you have plate collisions, you have glacial activity, and water erosion going on. So quite a bit of stuff to see at Acadia. So of course today, with the erosion going on, the Atlantic Ocean is eaten into the walls, in this case the basalts, where it has actually made what's called Thunder Hole. Why do they call it that? You just stand there one time when the tide's coming in, and you'll find out why it's called Thunder Hole. It's pretty impressive on the loudness of it. But a lot of beach erosion going on, a lot of cliff erosion going on by the Atlantic now in Acadia. Glacial formations, you have the U-shaped valley here, formed by the advancement of glaciers coming down through. You have striations on some rocks here from the rocks being carried by the glaciers, sliding over bedrock, which is where a geologist sleeps. You have erratics. Brittany has talked about erratic before, but this rock, for example, was carried by the glaciers and deposited to where it is sitting now. As you can kind of give a scale by this fence, just how large this erratic is. But again, the last geologic activity, other than the erosion, it was the glacial activity there. And of course, in my mind, the highlight of Acadia is going to Cadillac Mountain and seeing the earliest sunrise in North America. So it's a very popular thing to do if you're up there. Make sure you go up to Cadillac Mountain to see sunrise. It's pretty impressive, as you can tell from this picture. So as I said, this is the earliest sunrise observed in North America, because this is the furthest point east. Okay, kids holding the moon, and skydiver trying to land on the moon. And I go to Gettysburg. Last year we did a program on the geology of the Gettysburg battlefield. You might remember if you, again, have been here for a while. 3 million visitors each year, roughly. And the geology did play a major effect in the Battle of Gettysburg, as well as actually any Civil War encounter. The geology does play a role, just not Gettysburg. Devil's Den, that is the one of the type sites for the rock called Diabase. It's an igneous rock formed from magma, perhaps 4 to 5 miles below the surface at one time, 160 million years ago, roughly. And it's now at the surface because of erosion. But This is a classic site to see diabase. And the one thing about diabase is that it does not form a deep soil profile. If you dig down, if you have diabase in a yard where you might live, you can dig down more than 6 inches before hitting bedrock. You're lucky. So soldiers were not able to trench at Gettysburg. So they had to rely on rock outcrops or stone fences to hide behind for protection. Governor Warren, this is a statue on Little Round Top, which is another diabase ridge, part of what's called the Union Fishhook. His maneuver on spotting the Confederates heading toward Little Round Top on the second day of the 3-day battle is what many historians call the most important move of the Civil War. And so Governor Warren, who was actually an engineer and single man for the Union, recognized the Confederates coming through the woods carrying their rifles. And I won't tell the rest of the story, but it's pretty impressive how he got the Union involved up there to tell them, you better defend this spot right here because here they come. So as I mentioned, Gettysburg, basically the Union set up what's called the fish hook, which is mostly not all on this map, but it kind of hooks over here to Culp's Hill, down to Little Round Top, Big Round Top, and the Confederates were coming in from the west, mostly. And this is the Diabase Ridge. That's why the ridge is there, because of the diabase. And it was kind of determined by scouts before the war started that whoever won, particularly Little Round Top, was probably going to win the Battle of Gettysburg, because that's the highest point, the highest vantage point. And that's what really turned out to be. So here's the stone fences that were built. Some of these were built by farmers, getting rid of the rocks out of their fields. Others were built by soldiers, like overnight, particularly the ones on Little Round Top. This is South Mountain out here in the distance. That's how the Confederates made their way to Gettysburg, through the Caledonia Gap, the Cashtown Gap as it's called, to get to Gettysburg when they heard that there may be an encounter taking place. Virginia Monument is right here with Robert E. Lee. This is where Pickett's charge was centered. And you imagine Confederate soldiers lined up about a mile across here, ready for Pickett's charge. We're standing at the Union end of Pickett's charge. I thought these are neat pictures before. I'll show them to you again if you haven't seen them. Cave in Mexico with these giant gypsum crystals, person there for scale. And Rainbow Mountain over in China. This is real colored, folks. This is not, there's no false colors installed on these pictures. That's the way the sedimentary rocks are colored in Rainbow Mountain, China. Mammoth Cave. Before I take a break and give it back to Brittany here, Mammoth Cave, Kentucky. 522,000 visitors. Certainly it's a classic, huge limestone cavern. This is called the Staircase Tower here, where you come down the staircase to get into the deepest part of Mammoth. Rotunda Room. You don't see many formations, stalactites, stalagmites here. But this is just a big open room, very similar to what we saw up at the cave up there in Franklin County earlier in the spring. And then, as I said, it's a sandstone cap with the limestone under it. Older picture here showing you the formations. And there's 400 plus miles of passageway in Mammoth Cave. Some of these passageways haven't been mapped yet because they are just really, really too small to get through. But they have mapped at least 400 miles in this cave. So it's a huge cave. And here's a more recent picture of visitors looking at the formations. And you kind of get an idea of the scale here, but what I want to press onto you here is that for a formation to form like this, it takes about 100 years for 1 cubic inch of this material to form. So if you measure how many cubic inches there are, or we go on cubic feet of all these formations, there's a long time spent forming these through the dripping of water coming down through the sandstone and into the limestone. So incredible history at Mammoth Cave, Kentucky. So I'm going to pass it on over to Brittany, who's going to do a couple of parks and come back to me then. There we go, Brittany.
Alrighty. Well, Jerry forgot to add the word simple when he asked me to do some national parks, so I might have to cut some of this stuff out.
You're all right.
But some of the oldest rocks in the U.S. are actually in Rocky Mountain National Park, which is where I'm going to start. And the park's oldest rocks were produced when plate movement subjected sea sediments to intense pressure and heat. As we know that this results in metamorphic rocks, and the metamorphic rocks were schist and gneiss. They're estimated to be 1.8 billion years old. And later, large intrusions of hot magma finally cooled about 1.4 billion years ago to form a core of crystalline igneous rocks, mostly granite. I guess I'm going to do a slideshow. There we go. So the oldest metamorphic rocks are gneiss and schist. Here's a picture of gneiss from Flat Top Mountain. And here's a picture of the schist that's located in the park. The earliest rocks are igneous rocks. I didn't have time to get my sources on here, so any pictures that aren't mine and you're interested in, just email me. I can tell you what my source was. Moving on to the Paleozoic area. This is when the park was frequently submerged, lifted up, and eroded. Early in the Mesozoic era, approximately 1 million years ago, this is when dinosaurs were roaming the shoreline of the shallow sea in the area of the park. Animal remains were deposited in layers of sand, silt, and mud. And these sedimentary rock layers, including the fossils, are now exposed in the foothills to the east of the park. About 70 million years ago, the Rocky Mountain uplift began. Giant blocks of ancient crystalline rock overlain by younger sedimentary rock broke and were thrusted upwards. Streams started eroding away the sedimentary rocks and washed new sediments to the east and west of the park. During the Cenozoic era, we have faulting and more regional uplifting. And this is when the Rocky Mountain Front Range is lifted to its present height of about 5,000 feet above sea level. Some volcanic activity left young volcanic rock in contact with Precambrian rocks. And the volcanic rocks are seen mostly on the west side of the park. And this is an example. It's known as lava cliffs in the park. And then Mother Nature got real. If you were here for the vacation spots talk, you heard me talk about Rocky Mountain National Park and all the glacier features. Approximately, I think it was 3/4 of the park was covered by glaciers during this time. Next, I'm going to move on to the Great Sand Dunes National Park. So for many years, geologists were wondering, okay, where did all the sand come from? What caused these sand dunes to build so high? And finally, most geologists settled on the answer in 2002 when lake bed deposits on hills in the southern part of the valley confirmed theories of a huge lake that once covered much of the San Luis Valley floor. They named this body water Lake Alamosa. And what happened with this lake is that it suddenly receded after extreme water pressure broke through the volcanic deposits in the southern end of the valley. The water drained through the Rio Grande River, likely forming the steep Rio Grande Gorge near Taos, New Mexico. There were still smaller lakes on the valley floor, however, and large amounts of sediments from volcanic San Juan Mountains continued to wash down into these lakes, along with some sand from the Sangre de Cristo Mountains. Dramatic natural climate change later significantly reduced these lakes, leaving behind a sand sheet. Remnants of these lakes are still found today in the form of Sakwa wetlands. So the sand left behind after these lakes receded blew with the predominant southwest winds, and the wind was funneled towards three mountain passes here, the Mosca, Medano, and Music passes, and the sand accumulated in this natural pocket. From the other end, you have your storm winds coming in, and what they're doing is that these two opposing wind directions are actually what caused the dunes to grow so high, so vertical. And when you look at the Great Sand Dunes ecosystem, you're going to see a watershed, mountain streams that begin in the alpine peaks. You're going to have your dune field. The dune field is over 30 square miles. They reach heights of 750 feet. You're going to have your sand sheet. This is actually where 90% of the sand is. And then you're going to have your fragile plains where sand is cemented together by minerals left behind from seasonal wetlands known as sakas. So there's three basic types of sand that you will find in the Great Sand Dunes National Park. There's the darker fine grained sand that is primarily volcanic, and this traces back to the San Juan Mountains across the valley. This sand has traveled over 50 miles to reach the dunes, first on water and then on wind. And during the journey, the sand grains have been bounced and tumbled until they were polished in a process known as saltation. The coarse grains in the dunes actually come from the surrounding Sangre de Cristo mountain range, getting washed down. And it's also kind of neat because you can find black patches of sand, and this is actually magnetite sand, which is heavier than the lighter grained sand. So when the lighter sand blows away, you're left with these black large patches of sand, and it actually, as you can see here, can actually pick the magnetite up with the magnet, because we know magnetite is magnetic. So roughly 2/3 of the sand has originated as volcanic fragments from the San Juan Mountains. The remainder consists of particles of white and pink feldspar minerals and colorless quartz from the Sangre de Cristo Mountains. And there's also small amounts of gold that can be found at Great Sand Dunes. Next, I'm going to move on to arches. There is approximately 300 million years of geological history we could cover, but I won't do that to you. So what we're seeing here is actually the stratigraphy that you would find in canyonlands. Principle of superposition, youngest at the top, oldest at the bottom. The formations you're going to see in arches are going to be these three here: the Navajo sandstone, the Dewey Bridge, and the Entrada sandstone. The arches are formed within the Entrada sandstone, which was once a massive desert full of shifting dunes of fine-grained sand. The grains were nearly spherical, so when packed together, they formed a rock that was very porous. Drops of rainwater soaked into the pores easily and then slowly dissolved the calcite that was bonding the sand together. So in other words, these rocks were rotted from the inside out. And in the wintertime, the water in there would freeze, expand, and crack the rocks, and this is how the arches were formed. We have landscape arch, just to highlight a couple of the arches in the park. This is the longest span arch. It stands 306 feet. We have the tallest opening. This is the southern double arch. It soars 112 feet above ground level. This is known as the biggest balancer, and it's also known as Balance Rock. It is a massive sandstone boulder. It weighs approximately 3.6 tons. And to kind of put that into perspective, that would be the weight of an icebreaker ship or 27 blue whales. And of course, the most famous arch, Delicate Arch. This is the one everyone goes to arches to see. So since I was going to do arches, I decided that I might as well do canyonlands as well. For hundreds of million years, material was deposited from a variety of sources here. Southeast Utah was flooded by oceans, crisscrossed by rivers, covered by mud flats, buried by sand. The climate has resembled everything from a tropical coast to an interior desert. And until about 15 million years ago, most of the Canyonlands area was near sea level. Same thing with Arches and Rocky Mountain. We had uplift, and we know this as the Colorado Plateau. So here's this figure again, the stratigraphy here. The rocks in Canyonlands range from Pennsylvania to Cretaceous in age. We have our limestones and our conglomerates and dolomites down near being the oldest. And on top of that, we find the sandstones and siltstones. Today, Canyonlands is a high elevation erosional landscape where water and gravity continually draw material to the lower elevations. And if you have been to Canyonlands, then most likely you did stop at Upheaval Dome. And what's really neat about this is that geologists have debated for many, many years what was actually the cause of this dome here. And one theory is that there's a thick layer of salt. It actually underlies much of southeastern Utah and the Canyonlands National Park area. And when under pressure from thousands of feet of overlying rock, the salt can flow plastically, similar to when a glacier, ice moving at the bottom of a glacier. So as a result, over millions of years, the salt can flow up through the rock layers and form what they call a salt bubble. The other theory is the meteorite impact. Geologists believe that about 60 million years ago, this area was hit by a crater, and it caused a large explosion, sending dust and debris high into the atmosphere. Since then, there's been so much erosion, though, that any evidence of a meteorite has been washed away. So this kind of makes this theory questionable. But in 2008, it actually came out that some geologists discovered what they call shot quartz. And this is produced by the passage of high velocity, high pressure shock waves. So this got geologists thinking, okay, yeah, this is probably a meteorite impact. But we can't stop there, because there are also geologists who have suggested that after the meteorite hit, this disruption of the land is actually what caused the salt bubble, gave the salt the ability to work its way up through the rocks more readily, causing the salt bubble dome. Okay, and next, Black Canyon Gunnison National Park. This is very similar. You're probably seeing a trend here with these parks out west. We have our older Precambrian rocks down here. These are our metamorphic rocks. And on top of this, we have our sedimentary rocks. We have 70 million years ago again in this area. It's known as the Gunnison Uplift. And then we have more recent volcanic activity on top of our sedimentary rocks. What's neat about this, today, all of these rocks, these igneous and sedimentary rocks, are virtually eroded away. The river has carved through the softer volcanic material and then the sedimentary layers over most of the past 15 million years. 2 million years ago, the river eroded down to the harder metamorphic and igneous rocks of Precambrian age, and they got stuck, and they started incising downward in a more tight canyon form. So some of the rocks you're going to find at Black Canyon is a highly metamorphosed rock gneiss, very high in muscovite. You'll also find garnet, starlight, stalagmite, and you will also find schist. And there's two kinds of schist at Black Canyon. You have your mica-rich schist, and you have your hornblende rich schist. You'll also find quartz monazite at Black Canyon. And the steepness of the walls of Black Canyon actually owe their existence to this rock. The hardness of this quartz and the downcutting force of the Gunnison River have worked in conjunction for approximately 2 million years to carve the canyon. This rock is so resistant, and as the river cuts down, it makes the canyon deeper, and the hard rock keeps its walls from eroding and widening. The highlight of Black Canyon, though, is known as the Painted Wall. And if you've never been there, it's not one of the most popular, most visited national parks, but this is worth seeing. I've never seen a picture that does it justice. And you have your nice metamorphic rock gneiss with your pegmatite intrusions. It's just absolutely beautiful. It is 2,200 feet tall, making it the tallest cliff in Colorado. And just to give you an idea of how tall this shows it compared to some man-made features. We have number one, the Great Pyramids, the Washington Monument, the Eiffel Tower. This is Empire State Building. This is the Willis Tower, previously the Sears Tower. This is the Tokyo Sky Tree, and this is, the name is slipping my mind, but this is the tallest building in the world, the one that's located in Dubai. Alrighty, and I will go ahead and send it back to Jeri.
All right. Go back to where I was. All right, we'll continue our march here into our final 9 parks here. The Grand Tetons in Wyoming. Brittany was just kind of like in the neighborhood here, around the Grand Teton. 2.8 million visitors a year. Huge mass of granites and gneisses involved. Here's a metamorphic rock with a basalt dike going through it. Okay, and a dike is a body of rock that cuts through an older rock. So this is actually 2.6 billion years old rock, much older than what we talked about on the East Coast. So about 2.6 billion years, these rocks, in this case, the gneiss, were formed, and later with a dike going through it. Brittany talked about the plateau. This area is actually a lot of it formed by what's called an upthrowed fault block mountains, where there's been faulting and the block was pushed up or down. We weren't there to see that happen, but that's why the Rockies are the Rockies, and some of the other mountain ranges in the west are what we call block fault mountains. So this is actually a fault running up through here, the Teton fault in this case. So you might not be able to recognize it as a fault without the aid of a geologist. The Great Smoky Mountains, 10 million visitors a year. We'll be there in 2 weeks. And the Great Smokies do have a very diverse geology. If you can look at here, they have the metamorphic rocks, the gneiss, schist, slates, quartzites are all metamorphic. And there's also sedimentary rocks, which are the youngest rocks. So we have some ancient rocks that were granitic or sedimentary rocks at one time, like sandstone became quartzite from a ancient ocean. And then we have younger rocks that were made by an earlier ocean. And so rocks range from 1 billion years old to 200 million. So again, it's a huge range in that geologic time scale, 800 million years of a geologic time preserved in the Smokies. So it does vary wherever you go within the Great Smoky Mountains, what you're looking at. One of our favorite stops is Cades Cove, which is south of Gatlinburg by about 15 miles. It's actually a 11-mile one-way road that goes through the, I call it the Plateau. It does have historic cabins and churches off to the side that you can walk back to, plus a visitor center and a mill. But it's just a beautiful area surrounded by the Great Smoky Mountains, being a pretty flat area. You also these days regularly see bears out in the tree lines or in the fields if you're lucky. Hot Springs, Arkansas, another stop. 1.5 million people go there to get young, as they used to say with hot springs. And the reason it's hot springs is that it's kind of a tectonic event going on where we have faulting in rocks that are 420 to 320 million years old. And the thermal springs are in the hot spring sandstone, which is being produced by the faults coming up here. So again, if you're into that area, get to hot springs. 34 active springs in the area. There are some igneous rocks that were formed 120 million years ago. This is kind of a wintertime shot of the springs. Actually, not. This is not really a wintertime. This is actually the springs with the mineralization forming out of the groundwater. But about 1 million gallons water a day come out of these hot springs. Our next stop is back out west in Colorado, in Corsa Body, Corsa Pueblo Indian settlement made in sandstone cliffs. A very popular place. A lot of the Pueblos were built in these overhangs. If you never have seen a Pueblo village, it's pretty incredible where they lived, how they built them, and all that. So sandstone and shale overhangs again to keep them out of the weather. We would call this a big rock shelter. But this is one of the best preserved Pueblo villages. Mount Rainier. We talked about Mount Rainier and the Cascade Mountain Range and some other programs. Mount Rainier is a stratovolcano. In other words, one eruption is ash. The next eruption is going to be lava. 1.3 million people go to Mount Rainier. We do know that Rainier is getting warmer by the year, so it could be building up to an eruption sometime down the road. Maybe not in our lifetime. Of course, its sister Mount St. Helens belongs to the same mountain range in the Cascades, which has settled down. On Mount Rainier, there is a glacier. About 500,000 years ago to 1894 has formed. So again, if you like glaciology, you can also see that on Rainier. And just as a little side bite, there's this area of the United States in the Northwestern Territory, prone to be a high-risk earthquake region. With what's going on with the plate tectonics out here, there's a lot of movement, a lot of subduction going on beneath the North American plate. So it is a high-prone area. This is the Cascade Mountain Range volcanoes there. We moved down to the Petrified Forest in Arizona. These are some of the classic sandstone that you see like in the Badlands. which is kind of in the area of petrified forest. Most of the rock is Triassic in age, which is about 210 million years old. Of course, petrified forest, known for its petrified trees of ferns, cones, seeds. They do find fossilized insects and fish within the park also. Here's a picture of just a lot of petrified wood laying on the ground. It's amazing that these things are huge. And in fact, this is a restored Pueblo house that the national parks have reconstructed, but it's all made out of petrified wood. And it actually, there was actually a structure like this built. Again, as I said, the national parks have reconstructed it. So incredible place. Of course, it's illegal to take any petrified wood off the parkland, but in the old days, people have collected petrified wood, and you still may find some pieces in older collections of rock hounders. Also within petrified forest, not many people realize it, there's what's called newspaper rock. These are petroglyphs made by the Indians. There's like 2,000 drawings on the newspaper rock, and there's also a Pueblo ruin in the petrified forest. Again, so if you go to the petrified forest, make sure you check out everything. Zion in Utah, very similar to again, what Brittany was talking about a little bit. A lot of sandstone here, making up these layers, eroded by water that that flows through here more at one time. 150 million years of geologic history in Zion, 260 to 110 million years of history. Again, most of it sedimentary from shallow sea, pond, lakes, even a dry desert area with the sand dunes being now formed into a sandstone. So Zion actually has a pretty incredible history, geologic history also. Yellowstone in Wyoming, of course, a couple of different things it's famous for. The waterfalls, for example, is 308 feet high, 308 feet high. It does have volcanic rocks, fairly young in age when we talk about age of rocks, and I'm talking about 42 to 32 million years ago. That's very, very young compared to what we have talked about tonight. And of course, the erosion taking place. Columnar basalt, you remember that word before, columnar. This is some columnar basalts in Yellowstone. Again, formed like we saw in Hawaii and also the Skyline Drive. Yellowstone has formed due to we call it the super volcano, the caldera collapse. Okay, and again, based on our plate movement, you're able to see which way the plate in that area has moved. Here's the first caldera, 2.1, 1.3 was the second. The third caldera is 640,000 years old, and actually, it's kind of predicted that Yellowstone is going to have another eruption soon in geologic time. I'm not going to give you how long out we're talking about. We don't really know for sure, but within the recent geologic time, it can happen. So here at Yellowstone, here's the hot spot again. We have a continental hot spot, different than what we saw in Hawaii, but magma apparently is migrating upwards under Yellowstone, making this bulging a little bit more and then getting a little bit hotter with the hot water reservoirs, Old Faithful, the geysers going on. As this magma migrates closer to the surface, earthquake activity will pick up, which will be another factor that the geologists will be watching. Casa Grande, this is down to Big Bend, Texas. A lot of geology. Actually, if you've never been to Big Bend National Park, there's a lot of geology in Big Bend. Casa Grande is a old volcanic vent. This is actually was the vent. The cone's been eroded away, but this is actually the tube where the magma came out to form the lava. Okay, so 340,000 visitors to Big Bend, Texas. There is a large amount of sedimentary rocks again in the form of sandstone, as you're seeing here, from a mostly a lake environment, not really any ocean environments at this point in time. It was a lake, and of course they call it the Great Bend because the Rio Grande River does the big bend around the mountains, which I think in here this is the basalts that are making up all these highlands in here. And of course, there are some erosional remnants of the sandstone, similar to what you saw earlier from Brittany. You'll see actually there's cross bedding. Remember that word, cross bedding, from the Skyline Drive, the different angle of bedding going on there. So that could be that could even be a wind deposit in Texas, more of a sand dune than an ocean environment, which wasn't really going on here anyway. So I'm going to come back to you all after I show you these pictures to answer our question. We thank you for being here tonight, but I'm going to come back to you, and if you have a guess about what state was the last state to get a national park, you can type it into the chat room. I forgot to read a very cool quote about the Big Bend, Texas National Park. If you look on the National Parks website, they are describing Big Bend geologically. They say, great city block of stone and brick wrecked by an earthquake. And it goes on and says, perhaps order once prevailed there, but some mighty forces wrecked the place, shook it down, turned it over, blew it up, and set it on fire. That's how they describe Big Bend. So I'm seeing, okay, Georgia, Rhode Island, West Virginia. Diane, got it. Delaware. Okay, Delaware, only within the last couple of years, they got what's called the First State National Historic Park, which is in Newcastle.
Oh, what was that thing you said that people go to get young again, and it was in black and white? What was that slide?
Hot Springs, Arkansas.
Oh, will you show me that slide? Because I like the black and white.
Oh.
That was my parents' time, you know?
Okay, yep.
Because the first color picture came out in, what was it, 1861?
I don't know. Yeah. Anybody else have any other questions?
Would you show me the slide again? Oh, and I also asked another question in the chat about the other park in Virginia. The Virginia Park address.
Oh, you mean Shenandoah?
Is that Search Skyland Drive, or what is that?
Well, Skyline Drive goes through the Shenandoah National Park.
No.
But
what was that other Forever Young one? Black and white. Will you show me that one again?
What, Hot Springs, Arkansas?
Yeah, will you show me that slide?
Yeah, but I'll send that to you.
Okay.
Any other questions for either of us?
So yeah, I searched Skyland Drive, and what is it that I get? Skyland Drive where?
Virginia.
Oh, and then I get what?
Kathleen, just Google Front Royale, Virginia.
Oh.
That's the most northern part of Skyline Drive.
Oh, like your Royal, Front Royale. Okay.
Yep.
From Royal, yep.
Thank you.
One question that I kind of had to, it was kind of surprising because, you know, you're covering all these different national parks in the western United States, but I kept seeing the same formation names over and over and over again. Are they actually that widespread that you're seeing the same formation in multiple states? And
Yeah, that is correct. And I went through it pretty fast, but if you caught on, it was kind of the same geological history for, I think, out of 3 of the parks that I did.
Yeah,
like the Navajo Sansa and the Kayenta formation, I saw that in Grand Canyon and all over the place.
I forget the relationship, but there's a formation that's like the top of the formation is in one park north, and then the bottom of the Grand Canyon, toward the bottom of the Grand Canyon, that formation's the bottom in the Grand Canyon. So they're all horizontal out there. So they run for miles across the landscape there. That's a great observation you made there, Larry. You should get a special award for that.
Yeah. Dwayne's asking where the lava tubes were, Jeri. Were those actually from Hawaii?
Out of Hawaii. As I said, there's a number of them in the western part of the United States. Also, when I showed you though was Hawaii. So we showed you about a third of the national parks tonight. Okay, we threw a lot of stuff at you, I know, but that's what we get paid for doing.
Well,
we get paid? Oh.
No, I was like, Delaware was what, the last state to get a national park?
Yep, that's right.
What part of Delaware was that in?
Newcastle.
Wow.
It just happened.
Like it's new, right?
Yep.
Newcastle, like it's new, huh?
Just happened 2 years ago, actually.
Right.
So okay, well next week we're going to go shark teeth collecting. So it's Dr. Godfrey. That should be another great program. So I'll pass it over to Brittany and let her.
Where are those lava tubes again?
Hawaii.
What part of Hawaii?
Mauna Loa area.
Wow. My uncle went to Hawaii with his first wife.
Yep.
Too bad that it ended in divorce, but yeah.
Okay.
He liked Hawaii, you know.
There's geology everywhere you go. That's the last thing that you want to remember, right?
Yeah, my friend Mark Anthony wants to go to Hawaii, but his mother says, "Oh no, that's too far." Yeah.
All right, we'll let Brittany sign off here.
Well, thank you, Jeri, because as you know, I'm a huge national park lover, and I just think that they are absolute treasures, and I respect every national park. So I'm really glad that you put this together, and I put a little bit together. And thanks for coming, everybody. And to Andrew, I'm going to Maine in a couple weeks, so expect some text. So. Alrighty, everyone have a good week.
All right, we'll see you, everybody.